Hey everybody, welcome back. This disembodied voice that you hear is Jonathan Templin. I'm here with a lecture on simple marginal and interaction effects in general linear models, otherwise known as moderation. Let's get into it, shall we? In this lecture, we're going to talk about centering encoding predictors, interpreting parameters in the model for the means. Actually, going to define what the model for the means is. We're going to talk about main effects with interactions, and I'll give a quick general linear model or GLM example. Comparing what we would call regression and what we would call ANOVA, put in quotes to indicate that this is really a somewhat arbitrary distinction of where the names get in the way sometimes. So today's example, let's compare and contrast GLM as regression and ANOVA. Imagine there was a study examining the effect of a new instruction method on test performance. In this case, what we're going to do is we're going to dummy code the variable for instruction method, where the value of 0 equals old and the value of 1 equals new. Our outcome variable will be percent correct. Now, leaving apart the fact that this variable percent correct has to range between 0 and 100, we will treat this as if it were plausibly continuous throughout the entire range. In a later lecture, we may discuss how to more appropriately handle data with censored or balanced like that. But in this example, test performance, once again, new instruction, the effect of new instruction on test performance in college freshmen versus college seniors, where we will also dummy code a freshman being a 0 and a senior being a 1. Now, in this case, I'm going to name the variable name senior to indicate the 1 represents a person who is a senior in college. And I'm going to name the variable new to indicate the number value 1 indicates somebody is taking a class with a new instruction method versus an old instruction method. So let's imagine we were to build a linear model for test performance. Here, test is the percent correct on a test. We would have a model intercept, beta 0. We would have a model slope or main effect, multiplying the senior variable. So these are all the people who are seniors when that is a 1. We would have a slope multiplying the beta 2, multiplying the people who were in the new instruction method. And then we would have the interaction of the senior variable times the new variable times beta 3. Finally, we would end with an error term, E sub p. The subscript p refers to the person, the college student, individual college student who is in this class. And p is an index variable. So it starts with 1 for the very first student and goes up to the number of students that we have. Also, we would typically note here that error under this general assumption of the general linear model follows a normal distribution, or is just independently and identically distributed as a normal distribution with a mean of 0 and a variance sigma squared, in which case we would call this the residual variance because it's what's left over of test after we predict it with the senior variable and the new variable. So here in this table, you can see the 2x2 setup that we have. We have a column for freshmen and a column for seniors. We have the new method and the old method as well. The cell means represent the average score for each of these permutations of senior and new. So freshmen using the old method had a score of 80.2. Seniors with the old method had a score of 82.36 on average. Freshmen with the new method had a score on average of 86.96, and seniors had a score on average of 87.08. Now you'll note the numbers beneath the means happen to be the standard deviation of all the people who are in that cell, and then the numbers in the brackets represent the standard error of the mean, which is the standard deviation divided by the square root of sample size. In the columns of the table, you will see the marginal mean. So this is the mean of each variable without the influence of the other interacting or other variable as well. So the mean of all the students, both freshman and senior, in the old method was 81.28%. And the mean of all the students in the new method was 87.52. So it looks like the new method's doing better. Similarly, for the mean of all freshmen, regardless of which method they were in, is 84.08. And the mean for all seniors, regardless of which method they were in, was 84.72. And in this bottom corner right here, this is the grand mean. This is the mean of all students, regardless of freshman, senior, old or new method. Overall, on average, for this test across the sections would be 84.4. So let's talk a little bit about centering and coding predictors, because each of the predictors in this variable, in this example, were coded, right? And to do that, let's get into the two sides of a model. So here is that same regression equation, but just put with generic an x and a z, right? So we have our outcome variable yp, and we have a beta 0 plus beta 1 x plus beta 2 z plus beta 3 x times z. And in that orange box there, that is our focus in this lecture. That is what we call the model for the means. Why we call it for the model of the means? Well, once you condition on the value of x and z, it represents the expected or average value for everybody with that x and that z on the outcome y. Alternatively, the e that you see here, the error term up in this box, we will call the model for the variance. Now, it's not really much of a model because error really has a parameter sigma squared error right there, and we saturate it. There's only one place for a parameter, and we put one parameter there. It's kind of the least complex model that you can build for such an idea. Going back to the model for the means, or another way of putting that, the predicted values. And just a side note on that, predicted values are means. They are the predicted value of everybody that could possibly have that x and that z. The model for the means represents each person's expected predicted outcome as a function of their values on x and z and the interaction, each measured once per person. So each person gives us one piece of data, the test score in this example, and each person was in one of the teaching methods, new or old, and was either a freshman or a senior. The estimated parameters here, we will start calling fixed effects. Now, this distinction doesn't usually come into the general linear model until we get into mixed effect models, where we might have fixed effects that are both fixed and random, right? So this distinction for now, we're just going to leave to the side. We're going to get used to calling these fixed effects. In a later lecture, we will describe what that actually means a little bit further. But just know the following. They're not random variables. They're fixed. They don't follow a distribution. But as a consequence of our sample, we can rely upon statistical properties, the technical term for that being asymptotics, meaning as n goes to infinity, to come up with a theoretical, what we would call sampling distribution. So if we were to repeat this same experiment over and over and over again, what would the distribution of these look like? Now, the number of fixed effects will often show up in our formulas. So here, we're going to call that k, and we have 4 fixed effects here, beta 0, beta 1, beta 2, and beta 3. Now, in the model for the variance, again, I'll put model in quotes. I'll just do that right here. There is one residual, this error right here. Now, if you're only familiar with single level linear models, you will say, well, yeah, there's always one residual. But as we get more advanced, as we get into variance components or mixed effects models, there will be more than one residual, more than one dimension of sampling, really. Error, again, this little tilde represents what we would say error. The error or residual for a person is independently and identically distributed as a normal distribution. That's where this n comes from. Now, in the parentheses, there's 2 parameters to a normal distribution. There's the mean, which is always 0 in this case. And then there's the variance. In this case, we're going to denote that as sigma squared error. And what we're going to call this is the residual variance. The variance in all those terms that are left over after you do the predictions. Error, E sub p for a person, has a mean of 0 with some estimated constant variance. And oftentimes the constant variance is described, if you want the technical jargon or the thing that just rolls off the tongue, we call that homoscedastic variance. It's one of the hallmark assumptions of linear regression. And later in lecture, we will see that we can actually go and kind of weaken that assumption or make it more general later on. But here, error has a 0 mean, has a constant variance, sigma squared error, is normally distributed, is unrelated to both x and z, and is unrelated across people. That's that independence who we were talking about. So what we're going to do now is represent the effects of the predictor variables. From now on, we have to think carefully about how the predictor variables are entered into the model for the means. So what I mean by how in this case? How in this case represents the coding system or the centering point. Basically, for each variable, we need to know what 0 means. And it seems pretty obvious because we started the example saying, oh, yeah, we're going to call the new method 1, so therefore the old method of teaching would be 0. So we defined it. But sometimes we may have a quantitative variable where we have an actual 0, right? For instance, if I had height in inches, 0 represents a person has no height. That doesn't seem very relevant at the moment, but this is what we're trying to think about as we go through this. So why don't people always care? Often because the scale of the predictors does not affect the amount of outcome variance accounted for. So if we reset scale or if we change the coding scheme, if we, for instance, called the old method a 1 and the new method a 0, the amount of variance accounted for, r squared, would be the same. It also does not affect the outcomes values predicted by the model. So really nothing else changes. The residual variance changes, but what we've done is shift things around a little bit. And why this matters is because the intercept in this model represents the expected outcome when x equals 0, or when all predictors, in this case x equals 0 and z equals 0 in our model. Now, we can end up with nonsense values for the intercept if x equals 0 isn't in the data. So again, if you have height as a predictor in your model, a 0, and you did not center height, which we'll talk about in the next slides, the intercept would represent a person with 0 height. Now, most of the time, we don't necessarily care about the intercept, but centering in this case is really less important about the intercept in linear models that are these general linear models. When we start getting into more advanced models like multi-level models, where we might have a random intercept, the amount of variation around the intercept changes depending on where 0 happens to be. So as we go forward past linear models, we quickly need to understand what centering points might be. We'll so we can end up, again, with nonsense values if we're not careful for what our predictors happen to be. We will almost always need to deliberately adjust the scale of the predictor variables so they have 0 values that could be observed in our data. And that's in part, again, moving forward with an eye toward multi-level models or mixed effects models. But it especially matters when the case of interactions, and we're going to talk about that this lecture here. So for continuous predictors, we can make the intercept interpretable by centering. Now, centering, what we're talking about is what we're doing is subtracting a constant from each person's variable value so that 0 falls within the range of the new centered predictor variable. Typically, we might center around a predictor's mean, right? So we might say x, like for person 1, their x value might be x minus the overall mean of x1. The intercept is then the expected outcome for the average x1 person, right? So x1, I misspoke just a second ago. x1 represents variable x1, not person 1, but this is x1. A better way of doing that might be to center around a meaningful constant, right? So for instance, if we centered by height, then our mean height might be the sample mean for the sample that we have. Now, if we happen to find a sample where we have a set of really tall or really short individuals, this mean may not generalize. It may not pass. So alternative to that, you might say, oh, let's center around a height that seems to be relatively common, perhaps in a set of people, something like maybe 5 feet 6 inches or something along those lines. The intercept is then the expected outcome for a person with that constant, right? So now, because when x1 is 0, if we centered x1 has to be 0 when x1 equals c. So c now represents the value that the intercept it covers. It's the expected score for someone at a value of c. Expected, let's say, whatever outcome for a person who's at 5 foot 6 inches tall. For categorical or grouping predictors, we manually or our statistics program, data science program, will make the intercept interpretable by creating a reference group. Now, a reference group, this is all but one method of coding. We're going to talk about a couple other ones. This is sometimes called reference group coding or potentially dummy coding. The reference group is the group given a 0 value on all predictors created by the original grouping variable, such that the intercept is now the expected outcome or the mean outcome for that reference group specifically. So this is accomplished by setting a 0 and a 1, right? So if we had men and women, if we had sex assigned at birth, men and women, boy or girl, male, female, I really should say, this value 0 would represent the reference. And so whatever our outcome would represent the average score for someone who's in the 0 group. In the case of 0 is men, being men, that would be the score for men. And if you chose to put women equal to 0, then that would be the score for women. For more than 2 groups, what we need is the number of dummy codes to be the number of groups minus 1. So for instance, if we have an experiment where we have a control group and 3 different experimental treatment groups, treatment 1, treatment 2, and treatment 3, that one variable group would have to have 3 different coded variables to be entered into the model itself, right? So we might have D1 representing the difference between the control group and T1. So let's imagine control was always 0. Then the first variable would represent the difference between control and treatment 1. The second variable would represent the difference between control and treatment 2. And the third variable would represent the difference between control and treatment group 3. Here, the thing to note is, in the first variable, every value except for the place where treatment 1 happens to be is a 0, and treatment 1 gets a 1, the indicator that that variable refers to people in treatment 1, the treatment 1 group. The same is true about D2 and D3. The indicator just moves to indicate either treatment 2 or treatment 3. And here, this sequence of numbers 0001 refers to which group starting at control, treatment 1, treatment 2, and treatment 3, respectively. Now, depending on how you enter your variables in your software package, a lot of the time this is done for you, but not always. So we'll talk about that a little bit later too. Now, there are a few pitfalls with this. All predictors representing the same group must be in the model as predictors at the same time for these specific interpretations to be correct. So what I mean by that is our linear model here would look like y for a person equals beta 0 plus beta 1 times d1 for a person plus beta 2 times d2 for a person plus beta 3 times d3 for a person plus error for a person. Excuse my handwriting. I feel like I write in hieroglyphics, but hopefully it doesn't look like that. Not too much. Now, if we somehow omit, for instance, the third dummy-coded variable, like D3, then that means, think about that, it's like making everybody's value a 0 for that variable, and everybody we just defined who has a 0 is somebody in the control group. We've just combined the third treatment group and the control group. So we need to have all 3 or all of the dummy-coded or effect-coded parameters into the model as we put this through the analysis. Now, model parameters resulting from these dummy codes will not directly tell you about differences among non-reference groups. So in what we would get out of this approach here, let me see here if I just add beta 3 back here, D3P. Okay, beta 0, we just learned before, is the mean of the control group. What beta 1 represents is the difference in means between the treatment and the control group. Treatment 1 group, T1, and the control group. What beta 2 represents is the difference in means between T2 and the control group, and similarly with T3. So we only get 3 of the differences. If we wanted to get, for instance, the difference between group 1 and group 2, we wouldn't get that directly from our software, but we could go figure out how to do that based on these parameters, and we're going to show that in just a few slides. Now, you might be thinking, well, that was pretty simple. I've got 0s and I've got 1s for my group. And yes, that is pretty straightforward. But there are other types of coding. In fact, the codes that you give you, the numeric codes that you're giving, are arbitrary. And for any choice of code, so long as they're applied equally across all of the groups to all of the people in each group, will result in the same type of predictions. So, for instance, we could have chosen to assign our gender variable a negative zero point 0.5 for men and a positive zero point 0.5 for women, or vice versa. That type of coding system is sometimes called contrast or effect coding. And it has ramifications for how we interpret the regression coefficients, but I'll leave that for right now. We could also test other contrasts among multiple groups, right? So, for instance, if we have a four-group example, right? In our four-group example, let's imagine we wanted to compare our control group against the average treatment effect. Well, in that case, we might code a contrast where we would take the mean of the control group, assign it, and multiply it by -1, and sort of place a weight of roughly 1/3. This 0.34 is just a sort of rounding to make these numbers sum to 1. Rounding in the wrong direction, I should add. Anyway, these three proportions effectively weight the means of each of the other treatments right here. And so the result of this contrast would be sort of the difference between the control group and the average treatment effect across all treatments, treating them roughly equal. So what we were just showing on the previous slide, I actually have here. Categorical predictors, we can do manual coding, right? Where we code D1, D2, and D3. Again, the control group is 0, treatment 1 is 1, treatment 2 is a 2, treatment 3 is a 3, indicated by these variables, right? D1, D2, D3. The new variables here would be those three variables we showed in the last slide. And this equation was what I was trying to draw on that last slide in my hieroglyphics itself, right? So how does the model give us all possible group differences? Well, we can determine each group mean and then just take the difference, right? So we know, for instance, that the control group mean is beta 0. The mean for group 1 is actually the control group mean plus beta 1. And why do we know this? Well, beta 1 is the difference between the treatment 1 and the control group mean. So when we want to remove the difference, we just put these in together and we sum them up and we get our treatment 1 mean. And similarly, the same thing would work for treatment 2 and treatment 3. So the model for the four groups provides three differences, right? The control versus each treatment, but indirectly provides another three differences. We can go and find those other three differences, right? For instance, if we wanted to see the difference between the treatment 1 mean and the treatment 2 mean, right? So we have T1 minus T2 here. The T1 mean, I'm going to drop the D1 from this. I'll just put beta 0 plus beta 1. That's that one. And we subtract beta 0 plus beta 2. The beta 0's cancel, and we're left with beta 1 minus beta 2. That gives us the mean difference between treatment 1 and treatment 2. Now, similarly, we can do that for the difference between treatment 1 and treatment 3, and treatment 2 and treatment 3. And this slide shows what I was writing before. I'm foreshadowing a lot on these slides. It's like I've seen these before. Sorry, inside joke. Anyway, these are the group differences that we can get. Remember, we get three specifically from the model, beta 1, beta 2, and beta 3. The other three we can form through what we call a linear combination. A linear combination is a weighted sum, right? In this case, the weight would be 1 multiplying beta 0 and beta 2, and would be -1 multiplying beta 0 and beta 1, leaving us with beta 2 minus beta 1. Now we can do this in R, right? In R, turns out the linear model itself, this linear model syntax, allows us to enter each of these three separately. So y tilde d1, d2, d3, shown in the underlined section on my slide, describes the model where we have all three effects. There is a package called multcomp in R that allows us to go and then take the beta weights from our model and move them into configurations that would give us those contrasts, those differences between the other groups. So here, what we have to form is a vector of zeros and ones, depending on what we want to do. So I'm going to call mean 1 the control group mean. Control group mean, each of these numbers in the C in here is a number multiplying beta 1, beta 2, beta 0, beta 1, beta 2, and beta 3, respectively, right? So the first number in that C multiplies beta 0. The second number in that C, it looks like this. It multiplies beta 1. The third number is beta 2, and the fourth number is beta 3. So what you can think about this doing is if the C function down here is 1, 0, 0, 0, like the very first line here, if we multiply these together, I'll put a little multiplication symbol there, what we're left with is beta 0 plus 0, I guess this is a 1 times beta 0, 0 times beta 1 plus 0 times beta 2 plus 0 times beta 3, which just leaves us with beta 0. Right? So I'm going to call this the control group mean, because when I define a variable in R as the mean, I can use it in other places. So I'm just going to label that as the control group mean so that I can use that later on to try to think about differences between control and T1. Similarly, I will create a variable for T1 mean, the T2 mean, and the T3 mean. And now I can form my contrast, my difference between each of those means, right? So for contrast one would be the difference between mean 2 and mean 1. I just take the variable name, mean 2 and mean 1, and subtract them. And I can create row names for each as well. Similarly, I can do that for each of the 6 combinations that we see up here. Finally, when I have all those values, I use this, what's called an rbind function, which basically takes each of these sets of values, thinks about that as a row in a data set in R that's called a data frame, and adds each of those as a row in the same data set. And technically speaking, this is a matrix in R. I submit that matrix of my contrasts to the glht function, which comes from multcomp, and I can see the values after that. Okay, moving on. Actually, before I move on, let me also note that in the additional materials for this lecture, you will be able to find the R syntax and the data that I'm showing in this example, and you'll be able to rerun that on your own to see how it works. Okay, so what the intercept should mean to you. The model for the means will describe what happens to the predicted outcome y as x increases or as z increases. That's our typical way of putting it. But you don't actually know what y is supposed to be unless you know where the predicted values are starting from, right? The intercept itself is the u are here sign, so it should be somewhere on the map, right? This is a set of variables. Sometimes if we did not center math score, the intercept would be all the way down here. But if we centered it, let's say at the mean of math, the intercept might be right here. For continuous predictors, we will make the intercept interpretable by centering. I say we, that is not R. I mean, technically speaking, we do write R code for it, but we have to write the R code. It's not done automatically in the model itself. And again, centering is where we subtract a constant. Sometimes the sample mean, sometimes some other reference value, like I mentioned in the example before, a person of 5'6", or what is that, 66 inches tall. So we subtract this constant from each person's variable so that the value 0 falls within the range of the new centered predictor variable. The predicted group means that specific levels of continuous predictors can then be found using the same procedure, right? So if x1's standard deviation is 5, means would be plus or minus 1 standard deviation. So the main effects, now let's talk about moving forward, where we look at a model that has both main effects and interactions as well. So interactions between predictors is what we're going to talk about here. Interactions, technically speaking, are the regression coefficient multiplying two or more predictors that are multiplied by each other in the model itself. So literally, we're talking about a multiplication of one predictor times another. We're going to use that result to predict our outcome y. Oftentimes, we call interaction moderation, right? Why we call it moderation is that the effect of one predictor depends or moderates the value of the other predictor, right? So any of the interacting predictors could be the moderator. In our example, for instance, we might say, how does teaching method moderate the impact of being a freshman or senior on your test score? Or how does the class level, freshman or senior, moderate the impact of teaching method on your test score? Here again, the context matters, right? Both are true. You can have, because both variables show up as both main effects and interactions, you can close your eye and look at, for instance, X, which in this case was method being new or old, or you close your other eye and look at class a person is, freshman or senior. Now, some of the distinctions of these, what happens and how many predictors and how many interactions get included depends on how you're coding your software. If your software is following something like analysis of variance, by default, in this case, each of your predictors is categorical, so they get dummy or effect coded by the software. And then the software automatically adds all possible interactions. So if you have 2 categorical predictors, there will be 1 interaction. But if you have, 10 categorical predictors, there will be quite a few interactions. If you really want to know, think of it this way. For 10 predictors that are categorical, you would have 10 main effects. You would have 10 choose to, the combination 10 choose to. Two-way interactions, you would have 10 choose 3. Three-way interactions, you'd have a lot of parameters. In fact, the more categorical predictors you have in your model, the more interactions you have as well. That's when we're calling this quote unquote analysis of variance. Now, in analysis of covariance, right, this is where you'll have continuous predictors that are covariates, but also categorical predictors. Somehow, based on tradition, that's exactly it. Based on the tradition and where these things started, there are no interaction terms in the model itself. But I will say, without interaction terms, what that makes you assume is that the slopes for each of the continuous predictors are constant across values of the categorical predictors. So there is no change in slope. And in the old school texts about analysis of covariance, you will hear people say this is analysis of covariance assumes homogeneity of slopes across categorical predictors. But there's no reason it needs to assume that. We can just add those interactions directly into our statement. So in R, we would add the product of variables into the LM function statement as well. And finally, if you're in the regression mode of software where everything is assumed to be a continuous variable or just variables that you have coded yourself, there are no interactions that are automatically entered into your model, right? There is no default. You have to enter them all manually. So take your flavor of what's easy depending on the situation you're in. Now, what are main effects of predictors within interactions? Let's talk about those for a little bit. Main effects of predictors within interactions have to remain, should, but not just should, must remain in the model, regardless of whether or not they are statistically significant. Right? The interaction term from our example, beta 3, is either over additive, right? If it's positive, we call that over additive or enhancing, or sort of more than would be predicted by the other 2 variables, or under additive, a dampening effect if it was negative. So what is additive to must be included in the model. Or another way to think about it is this. Let's go back to the model on this slide in the beginning, right here. Now, in linear regression, you may have learned that when we have, for instance, beta 3 in a model along with beta 2 and beta 1, we're talking about the effect of the variable beta 3 is multiplying. Leave that aside for the moment. It's a product, but leave that aside. But that is now controlling for the influence of the other variables. So when an interaction is present, we have to control for the values of the main effect, right? So thinking about what we see on this screen, if we don't control for the values of beta 1 and beta 2, beta 3 may be significant for more than one reason. Beta 3 may be significant because the interaction truly is non-zero. Beta 3 is not 0. That's the one reason, and that's the one we want to have if we put an interaction in the variable model. However, if we don't control for the effect of beta 2 or beta 1, if, for instance, if these values were not in the model itself, then beta 3 also could be significant if beta 2 were non-zero, because the only way it can impact the variable itself is through beta 3, because z is right here now, but not being controlled for by itself. Same with beta 1. If beta 1 were significant, it could also give beta 3 its significance if it's not being controlled for. So think of it this way. We need to control for the presence of x and z by themselves if we're putting their product in the model. Because if we don't, we may get conclusions that are not accurate. There may not be an interaction between x and z, but if we don't put those main effects in, we will never be able to tell if the interacting variable truly is that interaction or not. All right, let's find that slide where I was at before. Here we go. So here's the main thing you can think about a two-way interaction. The role of a two-way interaction is to adjust the main effects. However, the idea of main effect no longer applies. Each main effect is now conditional on the interacting predictor. All right, so if we had a model of y being predicted by a variable w, x, z, and then the interaction between x and z, the effect of w is still a unconditional main effect because it is not part of an interaction, right? So it is the effect for everybody on y. However, the effect of x shows up here. X is predicting y by itself and is part of z. So the true main effect of x has to be when the influence of z is now gone, right? We have to basically make z 0 to eliminate this part of the x by z product. So the main effect of x is now called the conditional main effect, right? Specifically when z equals 0. And likewise, the same thing is true of z. The effect of z is now conditional on the main effect of x being 0. Or specifically, the effect of z is now the conditional main effect of z when x equals 0. So now you see, because the main effects depends on of variables in an interaction depend upon what the interacting variable's 0 point is. This is why 0 is important and why we keep track of that for every interacting predictor. Otherwise, we may get incorrect conclusions about what those main effects actually mean. It does change how you describe a main effect. And I can't tell you the number of times I've seen published papers where the main effect is interpreted as unconditional, like we'd say in W here, when really it is only true for when x is 0 or z is 0. The interacting variables are 0. Okay, let's see how this works in practice. Let's talk about model-implied simple main effects. For this example, let's imagine we're going to predict a student's GPA based on two predictor variables. One, the attitude of their parent as measured by a 5-point Likert scale between 1 and 5, where 1 is a very negative attitude toward education and 5 is a very positive, and 3 would represent neutral. And then the second variable will be a person's father's number of years of education. And let's also then take the product of a person's parental attitude and father's years of education and put those in an interaction. So given any values of the predictor variables, the model will provide a prediction for the outcome, right? So plug in something for attitude, for education, and their product, and you'll get a predicted GPA. But in addition to that, it will also provide any conditional or simple main effects implied by an interaction term. Now here, I've been using the term conditional for main effects in a model with interactions. Sometimes we refer to those as simple main effects, though. So I might use those interchangeably, and you might hear those interchangeably going on. And once again, that simple or conditional main effect is what the value happened to be originally. So for instance, 1 plus what modifies it. In this case, 0.5 times education. So how we figured this out? Step 1, 3-step process. Here we go. Step 1, identify all terms in the model involving the predictor of interest. So here, the effect of attitude, right, the slope of attitude, comes from all the places where attitude shows up. In this case, beta 1 times attitude, right here, and the interaction, attitude times education times beta 3. Then we could do a little bit of algebra and take out attitude from both of these parts of the sum and put that in front of what's left. So we see that attitude has a new slope of beta 1 plus beta 3 times education. So basically that term here in the parentheses is our new beta 1. And what you can see is a father's number of years of education really governs or drives or changes the effective attitude. Or another way of putting it, this education variable, the slope of attitude depends on it. It moderates it. It changes it. I'm using synonyms here to try to get the point across. Okay, so this new term in the parentheses is the new slope of the predictor at a given value of education. See, the slope is conditional upon the predictor. So why we call this a simple main effect is if that predictor is 0, this term goes away and we're left with simply beta 1. I hate the word simple because none of this is simple, but that's what it's called. Okay. Finally, step 3, we have to figure out how to estimate this or how to get numbers out of it. And you might be thinking to yourself, okay, no problem. If I put, if I wanted to see what the slope of attitude is for a value for a father who has 10 years of education, I'd take 10, right? And I'd multiply it by 0.5. So that'd be value of 5, and I'd add 1 to it. It'd be 6. And yes, that is the model implied main effect, or that is the main effect of attitude for a person whose father had 10 years of education. However, the standard error for that effect and everything that comes from the standard error, in our case, the p-value for that effect in a hypothesis testing context, are not so easy to calculate. So therefore, that's why we use functions like the GLHT function in R, which again comes from that mult-comp package. So let's try this now. Let's imagine a new reference point of attitude being 3 and education being 12. Here we go. All right, so let's plug in attitude 3, education being 12. Again, these are the 3 variables, y being the GPA of a student as a percentage grade out of 100, x being a parent attitude about education, again, measured on that 1 to 5 scale, and z being a father's level of education as measured in years of education. So here's our overall model. Here's our model with the coefficients that we just plugged in. Let's interpret some parameters. What does the intercept of 30 represent? The intercept of 30 represents the expected GPA for a student whose parent had a 0 value for attitude and had 0 years of education. So that's kind of odd. There may be parents with 0 years of education. That is entirely possible. Probably not likely in most societies, but it is possible. But the 0 of attitude is not possible because attitude's on a 1 to 5 scale. So kind of thinking that's a GPA for someone who has less than a negative attitude toward education. I don't know, but it's outside the range. So that's the intercept. Beta 1, okay, right here. So 2 represents the increase in grade point average per unit of attitude for a person with 0, whose father had 0 years of education. Again, notwithstanding 0 years of education is unlikely. What does that really represent? So as attitude goes up 1 point on the Likert scale, the GPA goes up 2 points. That's what that says. Right? And remember, this is the conditional or the simple main effect because it puts a 0 in the interacting variable. Now, we can do the same thing with beta 2. Beta 2 has a value of 1 here. It is the increase in GPA per year of education for the father, but that's for a parent with a 0 attitude for education. Right? So GPA goes up 1 percentage point for every year of education so long as the person has less than a negative attitude about education. So again, we recognize that 0 is important here. Let's go a little bit further and show why 0 is important when it comes to our moderators or our idea that how we can look at the interaction term itself. To really interpret that interaction, we can look at it in 2 ways. We can look at it as having, by the lens of attitude being the moderator. So basically, how does attitude moderate the slope for education? Or we can look at the lens of education as a moderator. How does education moderate the slope for attitude? Let's start with attitude as a moderator. the effective education, this slope right here, increases by 0.05 for each additional unit of attitude, right? So the slope gets bigger and bigger. The effect gets stronger as a parent's attitude about education goes up. Now, note what I'm saying here. I'm not talking about GPA itself. I'm talking about the impact of a father level of education on GPA, right? The change in the effect itself is what I'm talking about here. Likewise, I can talk about education as a moderator. So now the effective attitude, the slope of attitude, changes by 0.5 for each additional year of education, right? That makes it more positive, right? So for every year of a person's father has gone, had education, been an educated, that slope goes up by 0.5. Right? And how would we predict the GPA for an attitude of 3 and an education of 12? We just plug in those numbers overall and we get our predicted GPA of 66. But note, again, the interaction here, beta 3, we talk about it as really governing beta 2 and beta 1, not the GPA itself. Right? So it's kind of a meta level idea. So why 0 matters, though, as you can tell, that value that we plugged in there, a person with 0 years of, whose father had 0 years of education or who's had 0 attitude, uh, will matter. It doesn't seem sensical, right? The conditional main effects are on values that are not really plausible. In the case of attitude, it's absolutely implausible. In the case of education, it's very implausible for most societies. All right, so let's see what happens when we move the 0 point. Right? Let's imagine we don't center attitude, so we leave this untouched, but instead we center education level at 12. So in this case, it's like saying we are taking education minus 12. Right? And to denote this a little bit differently, in the previous model, we'll just denote education minus 0 was there. Right? It's sort of for a didactic purposes, to sort of describe what's happening here. Now, I would also want to center attitude, but I'm showing you this because I want to show you what happens to each of the terms when we only center one of them, right? What happened to beta 0? Well, in the centered model, beta 0 actually becomes 42. And why that's the case is because the 0 for education really represents a person whose value is 12, right? So here in this model, this conditional main effect, where attitude is equal to 0, subtracted 12, that means we got to add it back somewhere, and it gets added back here in the intercept. Now, why did beta 1 change? It was 2 before, and now it's 8, right? Well, it's changed because this slope is now conditional on where 0 is for the interacting variables. The slope of attitude is conditional upon the 0 point for education. And because education, we subtracted 12 of it from it, and really that constant multiplying it is 0.5, that's like half of 12. There's 6 units that are unaccounted for. It moved up 6 to make an 8. Now take a look, though, at the other terms. The main effect of education didn't change because we didn't center attitude. So nothing changes about it. Similarly, the two-way interaction doesn't change because there's no three-way interaction to moderate it. So the highest level interaction never changes regardless of centering, and only the conditional main effects, or the simple main effects, another way of putting it, for the other interacting variable change when you center one of those variables. Right? So what do you think would happen if which fixed effects would have changed if we centered attitudes at 3 but left education at 0? The same process would happen, right? So beta 0 would absolutely change. The intercept always changes when we center. Beta 1, that would not change because we did not change the interacting variable with it. Beta 2 would change, though, right? Because beta 2 would change because now we've modified or changed the 0 point of its interacting variable attitude here. Okay, so now the trick is, how do we get the model to tell us what we want? The original model, or the model equation, already says what y the intercept should be. So here's our original model up here. And the intercept is always conditional on when predictors are 0. But the model also tells us any conditional main effect for any combination of values for the model predictors. Right? So remember, the conditional main effect is the value of the main effect when the interacting variable is 0. Right? So using intuition, the main effect is what it is. So in this case, 2 plus what modifies it, right? 0.5 times education. That is what the main effect happens to be. And how we can show this mathematically is it's sort of like the rate of change of almost like with a partial derivative. Let's stay away from the calculus here for a little bit, though. We don't need calculus for this class for what we're going to do. But here you can see this is the effective attitude right here. It depends on education. This is the effective education. It depends on attitudes. And this is the interaction. It doesn't depend on anything because there's not an interaction above it, not a three-way interaction. Now we can use these new equations to determine what the conditional main effects would be given the other predictor values besides 0. So let's do this for a reference point where we have attitude of 3 and education of 12. Right? So now we're centering attitude at 3. We're centering education at 12. When we do that, the main effect of the conditional main effect of attitude, the centered attitude, is 8. We saw that previously. The centered main effect of education is now 2.5. And the interaction term is 0.5. It's unchanged. The new intercept, though, is 66. And you might note 66 was the value we got for the expected GPA when we just plug those in uncentered. That's not a coincidence. It's mathematics for you right there. So the expected value of GPA when attitude is 3 and education is 12. Remember, that's their 0. 0 point for each is the intercept. That's what it represents. What does the conditional main effect of attitude represent? It represents beta 1. So we have to think about what it was before, 2 times what it modifies it, so 0.5 times education. And because we centered education at 12, we have to add 12 to it to get to the 0 point, leaving us with a value of 8. Now, all this stuff, I'm not going to ask you to do this by hand. I don't expect you to do this by hand. I just want you to see what happens to the main effects when we change the center point of the interacting variables. That's the key of this lesson right here. Right? The software can do this for us if we set it up correctly. Finally, same thing working for the effective education. We saw that before, and the two-way interaction is always unchanged because there's nothing else to moderate it. Now, the point estimate, so the value of the beta weight, otherwise known as the point estimate, is important. I mentioned we could always calculate that. If we had a calculator or something else, you did some math, math and multiplication, but that doesn't tell us the p-value. Remember, the p-value, we need the standard error because the p-value, what we would call a Wald test, comes from beta over the standard error of beta, that ratio right there. So we need to figure that thing out right there. So even if the conditional main effect is not given by its model, it's not given directly by the model, right? Its estimate and standard error are still somewhere in the model. That's why I say it's implied. Somewhere in the model, it has the knowledge of what it needs to be. So we want to get what that new p-value is, the three options to get the new conditional main effect estimate and standard error. And I put this in order of what I consider the least to most annoying. The first way is to ask the software to give it to you. That's why I'm trying to teach you G, L, H, T, and R. But if you use SAS, there's something called the estimate statement. There's a test statement in SPSS. There's a new statement in M+. I can go on and on and on. Each software package has this. It's so fundamental to linear models. It's in every one of them. We could also, for instance, recenter our predictors to the interacting value of interest and then re-estimate the model and repeat that over and over again. The downside of that is that the more times we run that model or re-estimate the model, the more chances there's some type of mistake in our code. So we don't want to do that very often. We could also do hand calculations, but that one is hard unless we do a little bit extra work to get what we need to do the hand calculation itself. Right? And the reason why is the standard error of attitude is not as simple as multiplying main effect times attitude, main effect and interaction, or adding those together times the interacting variable. So the standard error, what we can think of its squared value, how we calculate it, how it is calculated, is this way. The squared standard error is the sampling variance of the estimate. All right, so let's just start there. So let's think of standard error squared. We can always work backwards to get what standard error is, but standard error squared is the scale that we have to work on. Think the difference between standard deviation and variance. And I previously mentioned in other classes how the variance itself is often the natural parameter in a distribution, similar to the covariance. So we work with variance in this case. Here, the new standard error is as follows, right? The new standard error comes from the variance or standard error squared of beta 1 plus the new standard error or the variance or standard error of beta 3 times the value of that education variable you want to condition at. But then the additional term to that is 2, the number 2 times the covariance between those two parameters. And that term is multiplied by the interacting variable. This term right here does not get reported in software without a lot of effort. These terms you can find by taking the standard error. The variance terms can be found by taking the standard error and squaring it, but the covariance, you can't find that. It's somewhere buried. So how we find that, or where these values come from, is something we call the sampling asymptotic covariance matrix. Again, this is what would happen in the limit as n goes to infinity. The sort of the sampling variance, if a way of thinking about it, sampling variance covariance matrix, so how the things would change over repeated experiments like this, is something that we grab this from. It comes from model properties of statistics. It's kind of an advanced topic when it comes to mathematical statistics, so we don't really talk about it much in applied stat classes, but this is where it needs to come from. The variance is a sum is always, so if we were to think about it this way, right, we have a sum of these parameters, beta 1 plus beta 3 times education being a constant here, the sum of two random variables, the variance of that sum is always variance of 1 plus variance of 2 plus 2 times the covariance in there. So here, this is because each main effect estimate, what each main effect estimate could be is related to what the other main effect also could be. And note that if a main effect is unconditional, right? If its interacting term were 0, then its standard error squared is really its variance of beta only. All right, let's move on to another example: regression versus ANOVA. So this is what things look like in what we would call dummy coding and regression. So let's go back to that example from the beginning of this lecture where we look at the test score, percent correct on a test, based on whether or not a student was a senior, whether or not there was a new curriculum, and the interaction between whether or not they were senior and it was a new curriculum. Here, I dummy coded these variables according to their name. So 1 represents senior versus 0 being freshman. 1 represents new curriculum versus 0 being old curriculum. And I'm entering those variables in the model as my dummy coded 0, 1 values. I then run the model in R using the LM function, and I use the summary statement to get output the coefficient table. My coefficient table shows an intercept of 80.02, or 80.2. That represents the average score for when all the predictors are 0. So that's for the average score for a freshman in the old curriculum. And then you can see the conditional main effect of senior. That is the change in the average score. In this case, the score goes up by 2 points for somebody who's a senior, but in the old curriculum. The score goes up by 7 points. So someone's in the new curriculum, but they're a freshman. And then the interaction between the two represents the change in either of those. It's negative 0.304. Remember, this term moderates both main effects. And if we want to look at this from analysis of variance table, we could put that model 1 object into the ANOVA function, and we would get our model analysis of variance table. And what you'll note here is that the interaction, so when looking at this, these p-values excuse me, let me go back to the coefficient table up here. The p-values in the coefficient table refer to this coefficient, each coefficient in line, right? So this is the p-value of the simple main effects. When you get to the analysis of variance, right? So the p-values in the table here are conditional on 0, right? On the interaction being 0, the interacting variable being 0. But the p-values down here, one is the same, the interaction is, but these p-values are not the same. And that's because the analysis of variance table looks at the marginal effect of senior or the marginal effect of new. Remember, the margin is the sort of literally the side column or row, the bottom row of the table. So this is comparing people in the new curriculum versus people in the old curriculum, regardless of whether they were senior or freshman. This is comparing people in the seniors versus people who are freshmen, regardless of whether they were the new and the old curriculum. This is sometimes what we call a marginal test. Depending on your field, your data use example, this may be of little use, this description. And philosophically, and that's, you know, we got a PhD, that's what the PH stands for in theory. Let's see how this goes, if I can philosophize my way through this. With this interaction being significant, it really means that these main effects, the main effect of senior is conditional on the main or on the value of new. So a marginal main effect of senior ignores that conditioning. So a lot of times people will say, wait a minute, I don't care about the marginal main effects. Because in the presence of the interaction, marginal means nothing. To really describe the impact of senior, I need whether or not new was in the model or not, what the value of new is. That is why marginal main effects sometimes lose their value in the presence of interactions. Okay, now we can then go and work with the GLHT function, right? We build our matrix of contrast that we did before, our mean for each variable, right? And then we can get our contrast estimate, our standard error. And you'll note those standard errors are the same. That's because the number of people in each group are the same. That just happens because this is an arbitrary simulated example. Similarly, they're the same because we assume residual variance is constant across each of the predictors, homoscedasticity. But this is where it comes from. And here, if you wanted to think about what the values to put in the C function are, you can just plug in what the predicted values are, what the values of your predictors are to get predicted values for each of these tests. Right, so here you want people who are freshmen in the old curriculum, that is zeros for each of the predictors. That shows up in our first line way up here, and similarly for each of the other three. All right, here's the table that we end up getting. Right? This is the table of output. These are each of the cell means that you can see in each of these 4 spots. And then you have the fixed effects here for each. And this is the table from the regression coefficients. Right, there's beta 0, which is your reference group, freshmen in the old method. Beta 1 is the difference between those two means. Beta 2 is the difference between new method and old method for freshmen. Beta 1 is the difference between seniors and freshmen for the old method. And beta 3 is somehow interacting in between, so I just stuck it in the middle of those. Now, we can also get model implied main effects. That is literally the value for whether or not we want the senior effect for old. Right? That is, some of these are in our model, some are not. Right? But we could also do that. So the senior effect for the new method, this is basically what's the difference between senior and freshman for new method versus old method. That's what this represents here. Right? And these are all coming from these interactions. You can build these terms. Because we're dealing with beta 1 and beta 3, that refers to the second and the fourth spot in the C function in R. And then we can get the difference between the two. So here, looking into this is the output from the GLHT function itself. What we see here is that the difference between seniors and freshmen, basically seniors are 2 points higher in the old method and almost a point lower in the new method. Similarly, we can think about what is the difference between new and old for freshmen. Freshmen in the new method are 7 points higher than freshmen in the old method, and seniors in the new method are 4 points higher than seniors in the old method. So you can get all those permutations and see how it works out. And again, this is the set of variables that we saw from our last slide as well. Only now you can think about if we really want the difference between these two, we have to go and grab it from our software right there. Okay. What we will also say with that, maybe equally important, is, and see, I've been teaching Bayesian statistics for a number of years, and now I'm going back to frequentist, so I have to remember the importance of p-values. Here, why that might be important is to say, okay, is there a difference between seniors and freshmen? Well, significantly, is there a significant difference, I should say? Well, that depends. In the old method, there was a significant difference. That p-value was less than 0.05, or whatever your favorite alpha level was, and so long as it's not smaller than that number. However, there is no difference between senior and freshman in the new method. And maybe that's a good thing. Maybe you're creating a curriculum where everybody you want to succeed equally. So that's what you're looking for. Of course, then again, you can't really prove a null, so that might not be a good thing, may not just have enough data. Anyway, going down the rabbit hole here, you can see all the different ways that you can, dare I say, subject your R syntax or your data to all the ways of looking at it here. Now, instead, we could then, if we do this in the ANOVA method in R, what we would have to do is treat senior and new as what are called factor variables in R. Factor variables go and take a categorical variable and provide the coding system for you. You can go run the model. The summary statement shows the coefficients. The ANOVA table shows the ANOVA table, the ANOVA result here. And here you'll note the combination here is a little bit different in how we see it. But again, the interaction p-value is the same between the two. But it does give you, or I did put in that interaction. So there are two types of conditional main effects that show up in each of these tables. I wanted to highlight those again. There's the simple or conditional main effects, right? These are specifically for a zero value in the interacting predictor. Now we want that meaning to be chosen deliberately, usually, but that would be important. And those are in the summary function. But the terms that show up in the ANOVA function are marginal main effects, right? This is what's done for you without even asking. In this, when you enter factorial variables in ANOVA, the fixed effect solution is not given by default, often not examined at all. And the omnibus f-tests are used to interpret main effects. Instead, what this does to try to provide is produces the average main effect in the sample, marginalizing across all predictors. Again, this loses its relevance in the presence of interactions, but sometimes is needed. So we're finally to the end of this lecture. I hope you're still with me, or I'm hoping that you can rewind and hopefully disentangle what I had to say. But to wrap up, the purpose of today's lecture in a interaction sense is to talk about how multiple variables work together to change effects in linear models. That's what an interaction does. We were here to examine exactly what we can learn about our model from model output. For instance, the meaning of fixed effects, or how to get model implied fixed effects, and the interpretation of omnibus significance tests. We also covered how to understand why results from named versions of GLM may differ. Named meaning regression, ANOVA, and COVA are all the same model, but depending on your software, or depending on how you enter variables into it, you get different output, right? So the linear model for the means plus the normally distributing error term is what these models are. You can fit main effects and interactions among any kinds of predictors, even if the software doesn't for you, like in regression or in ANCOVA. And when variants of the GLM or the linear model provide different results, it's likely because your predictive variables are being recoded, sometimes by you. Class and by is in SAS. In R, that's a factor code. Sometimes when you import data into R or change data frames, it may automatically switch variables to factor variables, and that causes some issues. You can always determine what type of variable is by the class function in R by putting the data frame $ variable name into class, and you'll get that. The conditional main effects and marginal conditional main effects do not mean the same thing. So they will not agree in an interaction. And again, by default, your software picks your model for the means for you, right? The quote unquote regression version is exactly what you specify, but ANOVA and ANCOVA tend to provide interactions for categorical predictors, but not in the ANCOVA case with continuous predictors. And finally, if you're trying this at R, here's a handy guide. Now, I didn't spend a lot of time in R here, so I'll quickly go over this. How do I tell it what my DV is? It's the first command in this function here. That's your dependent variable before the tilde. How do I tell it I have continuous predictors? You can assume those by default, but you can double check again by using that class function in R and putting your data frame and variable name after a $ into it. And it should tell you numeric for continuous or factor for categorical. Likewise, again, if you have categorical predictors, that's that same function. If you want to get what fixed effects you want, you can use GLHT if they're not directly input into the model. The model implied is what I've been calling it in this lecture. How do I tell it to show me my fixed effect solution? I use the summary function once I apply it to the object that comes from LM. And how do I tell it to give me means per group? I can use GLHT or the factor type of variable if it's applicable. And how do I estimate model implied effects? I can use the GLHT function. And that brings our lecture to a close. Thank you for paying attention.